Hello everyone. So in this video, we are going to talk about the most general solution to the electrodynamic problem for arbitrary sources, arbitrary localized sources. So what we would be interested in doing here is to write down a solution for the electric and magnetic field when we have some arbitrary charge density or current density. Okay, so these are some arbitrary localized charge density and current density. And let's say we are given some arbitrary localized charge density and current density, then we can ask what is the solution of the electric and magnetic field, and this is what we are going to try to address in this particular video. Before we go ahead, let me begin with a very quick and brief recap of the idea of the vector potential and scalar potential, which we discussed in the previous video. So to start, we have the Maxwell's equations, and these Maxwell's equations are supposed to tell us what this electric and magnetic field are in terms of the sources. So given some charge density or some current density, we have to solve this equation to know the electric and magnetic fields. And apart from this, the set of fundamental equations also includes the Lorentz force law, which basically tells us what is the what is the force. This Lorentz force law tells us what is the force experienced by the charges when they are exposed to some electric and magnetic field. Okay, so here I have written it in terms of a density, which you can integrate to know what the force is. Okay, so this we have seen before. These equations we have seen a lot of times. So, and in various situations like electrostatics and magnetostatics, we have actually solved these equations and found nice explicit solutions to these equations. There also we have seen that for arbitrary time-independent charge density and current density, we could express the electric field and magnetic field in terms of an integral of these given charge density and current densities. That is exactly what we aim to do here, but now everything can depend on time. The electric field, the magnetic field, the charge density, the current density, everything here can depend on time. And of course, they depend on space variables as well. But earlier we were making assumptions such that things don't depend on time, and that simplified our life a lot. But here we will now consider that everything depends on time. And we want to solve this problem. Okay, so very good. So in order to solve this set of equations, the first step that we took was to introduce the idea of the scalar and vector potential. So what we did was, so we looked at this condition on the magnetic field, or this Maxwell's equation, which tells us that the divergence of the magnetic field is equal to 0. This equation immediately tells us that the magnetic field can be written in terms of a curl of a vector potential. This is the same thing that happened in magnetostatics, but also even when the magnetic field is time dependent, we can do this because even in that situation, the magnetic field has divergence which is vanishing. So therefore, we have to, we can always write this. The magnetic field can be written in terms of the vector potential, and the only thing new that is here is that the magnetic field as well as the vector potential can depend on time. That is the only new thing that is there in our discussions now. So similarly, if we take this fact that the magnetic field is written in terms of a vector potential and plug it into Faraday's law, okay, then we see that in Faraday's law, we can we can write the electric field in terms of the time derivative of the curl of A. Okay, now we can exchange the space and the time derivatives. That is always possible because these are independent variables. And if we do this exchange, then we can take this term on this side of the equation and write it as a condition on a vector. So this vector is this combination, electric field minus time derivative of A. So this vector must be curl free, and this follows explicitly from Faraday's law. Therefore, because this vector should be curl free, so we can always express such a vector in terms of the gradient of a scalar. And once we know that this vector should be curl free, this combination, where this A is the same A that appears in the magnetic field, mind you. It's the same A. So with respect to that, we can write this vector as the gradient of a scalar. This is the same thing that happened in electrostatics. Only in electrostatics, because things were time independent, this was not there, and we didn't talk about any vector potential. But now, because things depend on time, this term will be there, and we will have the electric field expressed in terms of the scalar potential. This is again very similar to electrostatics, but again this term is new. Okay, because it is this combination which is curl free. Therefore, we can write this combination in terms of the gradient of a scalar field. So therefore, the electric field now becomes, it has two terms, not only the scalar field, but also the vector potential. So the vector potential determines the magnetic field completely, but the electric field is not completely determined by the scalar potential in the dynamical scenario. It also has a contribution from the vector potential as well. Okay. So under this, again, I must mention that this minus sign is a convention, as we saw in electrostatics. It's the same thing. So basically, we want our conventions to be consistent with the conventions that we had in electrostatics. So therefore, we choose the minus sign here. Very good. So right now, with this definition of the magnetic field and the electric field in terms of the vector and scalar potentials, one thing immediately happens, which is very nice, which is these two equations. Remember, these were the Maxwell's equations without any sources. This is something very important, as you will see later on, that this is the Maxwell's equations without any sources, and these are immediately solved. As soon as we write the electric and the magnetic field in terms of the scalar and vector potential, these are immediately solved in the sense that they are satisfied. Okay, because the divergence of B, the divergence of curl of A, the divergence of a curl vanishes. So as soon as I write B as the curl of A here, the divergence of a curl vanishes. So this equation is satisfied. And also when I write E in terms of this in this form, and if we plug E back in here, then this first term vanishes because the curl of a gradient vanishes, and this term gives us the magnetic field back, and therefore right hand side and left hand side are same. So these two equations become identities, and we don't have to worry about these equations anymore. Okay, so we have to worry about two more equations, the equations that had sources, and that was the Gauss law and the Ampere's law. So let's see what the Gauss law and the Ampere's law has to say for the scalar and vector potentials. So the Gauss law, what it does is, so we take E and plug in this definition of the electric field that we had here. We plug it back in here in Gauss law, and that if we do, again I have taken the sign out and put it here. So if we do, we get this equation for the scalar and vector potential. This is just a scalar equation, so this is just one condition. And then if we use Ampere's law, then in Ampere's law we have made the substitution that this B is curl of A, and this E is this quantity here. And then if we just made some simplification, so basically we just regrouped certain terms, and then we put this combination together, which is the same combination as appears in the wave equation. The wave equation we have already seen while discussing electromagnetic waves in the previous video. So that is the same combination that appears. So we have kept that combination out, and apart from that combination on the vector potential, there exists this term here, which is like the gradient of a complicated looking term. This is like the divergence of A plus 1 over c square del phi del t. And so basically these are the two equations that one need to solve. Actually there are four equations, because this is a vector equation, so it has three components, and the one following from Gauss law is a scalar equation. So there are four equations, and there are four variables, because phi is a scalar field and A is a vector field, so it has three components. So in all there are four variables that we want to solve given any source. That means this is given, that the charge density and the current density, these sources are given, and we want to solve the phi and A in terms of charge density and current density through these equations. So we can always do that. And once we find a solution, we can go back and find the electric and magnetic field. But there is a very interesting phenomena that goes on, and this brings us to the idea of gauge transformation and gauge redundancy. Again, we have discussed this very thoroughly before. But again, let me just go through this point once. So what here, what goes on here is basically the following, that if we take a particular scalar field, any scalar field, okay, chi, which is a function of space and time, and if we transform the vector potential in this way, that we change the A to A plus gradient of the chi. The chi is a vector field. And at the same time, if we also change the scalar potential in this way, that we shift the scalar potential as the time derivative of the same chi. This is the same scalar field. Okay, so there's just one scalar field here. Okay, that is chi. So if we do this transformation, then we notice that the electric field and the magnetic field remains invariant under this change. Why does it remain invariant? So the magnetic field is a curl of A. So because this is curl of A, therefore if we shift A as with this gradient of some scalar field, then the curl of the gradient is 0, so it remains invariant. Okay, so why does the electric field remain invariant? The electric field remain invariant because there are two terms, and both this term has contribution from some chi when we do the transformation. Okay, so the phi has this contribution of the time derivative, and the A has the contribution from the gradient of chi. Now if you see that the signs are so adjusted that these two additional terms, this term and this term, they have been clubbed here, and you see, they cancel with each other because we can exchange the space and time derivatives. We can bring them through the time derivative, we can bring through the space derivative, and therefore these two terms cancel each other, and therefore the electric field also remains invariant. So we see under the gauge transformations, so this is the gauge transformation, which is parameterized by the scalar field chi. Under such a gauge transformation, we see that we see that this electric field and magnetic field remains invariant. And what describes a physical situation is the electric field and magnetic field, and not the scalar and vector potentials. If you like, scalar and vector potentials were introduced to solve, if you like, two of the Maxwell's equations. This the divergence of B and the Faraday's law. They were solved if we introduce the scalar and the vector potentials. But physical situations, they are described by the electric and magnetic fields, and these electric and magnetic fields are invariant under this transformation, which changes the vector and the scalar potential in this way. Okay, so therefore this transformation is a redundancy of description of a physical situation. So if we want to see this pictorially, what we mean is, as we have seen, the scalar and vector potential satisfies this particular set of equations following from Gauss law and Ampere's law. Okay, so let's say we solve this equation for phi and A given some sources. Okay, so that for various given sources that would describe a physical situation. Let me write the physical situations in terms of these crosses. Okay, so all these crosses represent a set of solution for phi and A. Just to give you a pictorial description of what is going on. So if we represent solutions, physical solutions, to this set of equation in this way, we will find corresponding to every physical situation which we have represented by a cross, there exist many solutions like this. Okay, there exist many solutions like this. Okay, where every point on the line is characterized by a choice of the scalar field chi. Right? Because every physical situation you can take that solution and then do a gauge transformation that becomes a new solution which describes the same physical situation. Okay, so therefore all these solutions are related by certain gauge transformation for a particular choice of chi. So if you remember, if you like, every point here represents different chi's or different gauge transformation scalar field. That thing is different, and for every choice of chi you can get various points on this line, and this whole thing together represents one physical situation, because all of them are related by gauge transformations, and therefore all of them represents one unique given situation. Okay, so the description in terms of the scalar, or in the description of the physical situation in terms of the scalar and the vector potential is not unique, although the electric and magnetic fields, they uniquely describe the physical situation. Okay, so if you compute the electric and magnetic field for all points here, which denote the solutions of this equation, okay, then the electric and the magnetic field will come out to be the same, because different points here are essentially related by a gauge transformation with respect to some chi. Okay, so if you like, this whole thing is a solution. This whole thing is a solution to this. This is the space of all solutions to this set of equation here, this one and this one, right? So if we have this set of equations, we can solve it, and then this will be all the solutions. But then various solutions would be related by gauge transformations like this. Okay, various solutions would be related by gauge transformations like this, and therefore there is no one-to-one correspondence between the solutions in terms of phi and A and physical situation. There is no one-to-one correspondence. The same physical situation is described by uncountably infinite number of solutions for phi and A, which are parameterized by this scalar field chi. Okay, the gauge transformation scalar field. So in order to solve this problem, okay, why am I saying this problem? What we want to achieve is we want to give the physical, we want to describe physical situations, and there has to be a one-to-one correspondence between the scalar and vector potentials, the solutions of the scalar and vector potential, and physical situations. If we want a one-to-one correspondence, then we have to choose one single point from these lines like this. Okay, so we have to somehow choose one single point here on these lines, and that would be essentially fixing what the chi is in our language. That would be fixing the chi once and for all. And so basically, therefore, if we fix chi, then we will choose one point on this gauge transformation on this line, and that single point on this line for all these solutions would describe the a unique physical situation, and there will be a one-to-one correspondence between the solution space of phi and A and that of physical situations. Okay, so you see. So this is what we are going. So physical situations are described by to summarize. So physical situations are described by the electric and magnetic fields, and for unique physical situation there exists a unique electric and magnetic field configuration. Okay. So now the question is, what happens in terms of the phi and A? What happens in terms of the potentials? The potentials, on the other hand, cannot describe a single physical situation uniquely, because we have seen that if we gauge transform that new potential also describes the same physical situation. All the points on this line describe the same physical situation. But in order to describe the physical situation uniquely, we have to make a choice or put a condition on, put an additional condition apart from the dynamical equations, put an additional condition on the gauge fields on this potentials, put an additional condition on the potentials phi and A, so that the solutions of phi and A with that additional condition describes physical situations uniquely, and there's a one-to-one correspondence between the solution space of phi and A and physical situations. I hope this point is clear to you. It's very important. So geometrically, what we have to do is we have to somehow pick a set of points, or take a slice on this and pick a set of points on these lines, so that this slice intersects the lines only once, and uniquely if they intersect. So every point here, so all the points here on this slice, they describe one given physical situation. And if we take this condition, so this slice is like taking a gauge condition. Okay, pictorial. So this is like taking a gauge condition, such as you have already seen the gauge condition, which is the Coulomb gauge condition, which says the divergence of A is 0. Let's say that condition is basically this slice. So this slice again is not unique. You could have chosen some other slice which can be in a different way, and that is also a valid choice. valid gauge condition choice, and that also fixes our problem. That means it fixes chi, and therefore it allows us to describe physical situations uniquely in terms of solutions of phi and a. Okay, so this, I hope the picture is clear, that we want this to happen. So we want to take this additional condition so as to cut down on the space of solutions that are allowed by these equations. Okay, so these equations allow a larger space of solutions than the number of actual physical configurations. Or if you like, if you compare this space with the space of electric and magnetic field, then, or space of solutions of electric and magnetic field, then the space of solutions of electric or magnetic field is much smaller compared to this space of potentials. If we just see, because there are many points on the for the potentials which corresponds to the same value of the electric and magnetic field. Now, if we put an additional condition to get rid of this redundancy, then there becomes a one-to-one correspondence between the solution space of phi and a and that of the E and B fields. This is what we want to achieve, and that's why we choose a gauge condition. Okay, so but here in this dynamical scenario, we see that there's this term in the Ampere's law which is very complicated, and we want to somehow get rid of this term and choose a condition suitably so that we can get rid of this complicated term. This we have seen before. In magnetostatics, this term was not there, the del phi del t term was not there. So we could choose this gauge condition, which was this Coulomb gauge condition, and we could make our life simpler. But here, in order to make our life simpler, we have to set this whole combination to 0. Only then this equation simplifies. Okay, only then this equation simplifies. But I must emphasize here that even in the dynamical scenario, this is very important. So please play carefully. Even in the dynamical scenario, the gauge condition, which is the Coulomb gauge condition, is a completely valid condition. Okay, but it so happens that there is another gauge condition that we can also choose, and this is basically setting this term to 0, and that has a name. It's called the Lorentz gauge condition. Okay. So basically, I have written these two conditions together. They are the most popular conditions, and they can be chosen. The Lorentz gauge condition is the one that simplifies life, as you will see. Okay, it simplifies the equations. So it is, somewhat more popular choice when you are talking about dynamical situations. But the Coulomb gauge, or this condition, the Coulomb condition, this is also a valid choice of gauge, or this also serves the same purpose as it served in magnetostatics. That is, it determined, it took this slice and it determined for us the vector potential uniquely in terms of a physical situation. So that is what happens here. Okay, here we are talking about both the vector and the scalar potentials together. So when I say that there is a cross here, which is a solution of the vector and scalar potentials, this represents the full solution for phi and a together. Okay. Very good. So now, if we take, so basically this Lorentz gauge condition, so both are valid conditions in this dynamical scenario, but this Lorentz gauge condition also serves, apart from simplifying the equations, it also serves as a way to ensure that the equations are manifestly Lorentz invariant. Okay, so by Lorentz invariant, I mean relativistically invariant. Okay, you will see later when you write down our relativistic transformations. We will see that at the end of this course, that in one of the useful things for choosing this Lorentz gauge, one of the useful things that happen is it maintains manifest relativistic invariance. Or covariance rather. Okay. So this is something which therefore is a in some sense, if you are thinking about the relativistic dynamics, so this is something which is slightly better choice of gauge So basically, in all our discussions for dynamical electrodynamics, we are going to stick to the Lorentz gauge instead of the Coulomb gauge. Okay, so as we discussed in the previous video, so there's a question whether or not the Lorentz gauge fixes the gauge completely, and the answer to that question is no, because if you see that if you do a gauge transformation with a chi, which is a solution to this wave equation itself. Okay, so this wave equation, the solutions to this wave equation is not unique, and we saw that there is a non-trivial solution to this wave equation. And once we take some of those non-trivial solutions to this wave equations and do a Lorentz transformation with such a chi, then we see that this condition, the Lorentz condition, this remains invariant. You can just go through the steps and you'll see that we get this additional term, which is the wave equation, and that vanishes. And because it vanishes, therefore, the Lorentz condition is invariant under a gauge transformation where the chi is chosen to be a solution of the wave equation. So so basically the Lorentz gauge is not a unique gauge choice, so it leaves out certain amount of redundancy. Okay, although it fixes a lot of the redundancy, but it leaves out. So basically, the redundancy was true that you could have chosen any chi, any scalar field. After choosing the Lorentz gauge, you cannot choose an arbitrary chi, but you can choose a chi which solves the wave equation. That is a restricted class of functions. Okay, so this restricted class of functions you can choose, and still you can be in the Lorentz gauge. So the Lorentz gauge is a class of gauge, if you like. Okay, so it is a class of gauges, or is a class of gauge conditions. So apart from this condition, you have to impose more criterion in order to fix this chi, so that you make a unique gauge, so that the gauge choice is complete. Okay, otherwise it's an incomplete gauge choice. Okay, so the Lorentz gauge choice is an incomplete gauge choice, and that is because of this particular fact. And so basically it describes a class of gauges rather than a single gauge. Okay, so basically this is one very interesting thing that happens. Now coming back to this equation for the phi and A, as we have seen, if we choose the Lorentz gauge condition, this term vanishes, and then we are left over, this is equal to the source, that equation. And also, you will see that the Lorentz condition tells us the divergence of A is basically given by 1 over c squared del phi del t with the sign. And if we take this and plug it back in here, then we find that both phi and A are described, or they are solutions to the inhomogeneous wave equation. So this is the wave equation for both phi and A, and this is the sources, the charge density and the current density. These are the sources. So this becomes the inhomogeneous equation for phi and A, and so this is another reason, if you like, which another nice thing that happens in Lorentz gauge choice, and that basically keeps both phi and A in the same footing. So it keeps both phi and A in the same footing as because they satisfy the same kind of equation, which is the inhomogeneous wave equation. So now what we have to do is to learn how to solve this inhomogeneous wave equation. Okay, that is what we are going to do now. Very good. So basically I have schematically written. So basically, if you work in Euclidean, if you are in Euclidean space, and if you are working with the Cartesian coordinates, then these are essentially four set of equations, four set of identical inhomogeneous wave equations. So if you know how to solve the inhomogeneous wave equation in flat space, then basically we would have solved the electrodynamics problem completely. Okay, so let's just try to do that. So this equation, therefore, I have schematically written like this. This chi represents, if you like, the components of the vector potential and the scalar potential, and this fx, this thing, this is the source. This simultaneously represents, if you like, the charge density and the current density. Again, this choice of minus 4 pi is a convention that I am making. Again, we have to account for that when we write down the solution for the scalar and vector potentials. But this is the equation that we want to solve, let's say, okay. So I have just put in this factor so that, you know, it doesn't become an annoying factor that you need to carry around. So we have put in this factor here, okay. So very good. So now we have to solve this equation. That is our purpose, okay. So if you have to solve this equation, then the first step, if you have to solve this equation, is to solve a different equation rather than this equation, or rather solve a specific equation like this, inhomogeneous equation like this, where the source, instead of an arbitrary source, is the delta function source, okay. And that particular solution to that problem is called the Green's function corresponding to this operator, okay. So if you like, it's, you know, schematically, it is the inverse of the operator. I'm saying that because if you think of this equation as something like a matrix equation, I'm sorry. So if you think of this equation as something like a matrix equation, that's some matrix on some, you know, another matrix, you know, so this is like a, you know, M is like a square matrix, A is like a column matrix. So this is equal to identity, okay. If this is the equation, then basically A, right. So basically A is given, right. So, right. So this would imply that A is basically given by M inverse, right? And now, so this, therefore, if we know the inverse of this matrix A, then we immediately can solve a problem which is, let's say, you know, if there's a if now we have a problem which is M times B equal to, again, some matrix here, let's say M times B equal to some source S, then we can, if we know the inverse of M, which is given by A, you know, we can immediately say that B is nothing but this A times S, because if we know S, A, then we know what is, if we know A, then we know what is S, okay. So this is exactly what we are trying to do here. Again, this was just a schematic understanding of what is going on here. This is, again, this is happening as functions, not as matrices. So basically this Green's function is something like the inverse of this operator here. So the Green's function is something like the inverse of this operator here. And if we are able to find G, therefore we have found the inverse. And then for any problem, we can just invert the operator and add the Green's function on this F, and that will give us a solution. So more explicitly, this step can be shown in the following way, that if we have you know, we can write down a particular solution immediately. So if we know what this G is, we can immediately write down a particular solution for this equation. And how is that? So that is given in terms of this integral, where we integrate the source with the kernel, which is G, okay. So why does that give us a particular solution? Because if we now take this operator, you know, this wave equation, you know, this operator, Laplacian minus time derivative, you know, if we take this operator and act it on this psi, if we take this operator and act it on this psi, then because psi is given by this integral out here, okay, because psi is given by this integral out here, therefore this operator is basically, here the x is the variable because psi is dependent on x, so that can be taken inside the integral, and because it can be taken inside the integral, therefore it can act on this Green's function here. This is the kernel of the integration, and if it acts on the Green's function, then immediately it will give me a delta function like this, because this is by definition the Green's function is a solution to this equation. And once it gives me the delta function, you can perform the integration and see that this is given, the source just comes out. And again, this is a local equation now. This x is the same thing as this x. Okay. So therefore, this allows us, the G, the knowledge of the G, allows us to immediately write down a particular solution in this form. And therefore, before solving this particular solution of this equation, okay, so any solution of this equation can be written as a sum of the homogeneous part and plus a particular solution. And we are basically interested in the particular solution because the particular solution is the one that has the information of the source. So we want to find the electric and magnetic fields given some sources. So we are very much interested in the particular solutions. And because of that, that particular solution can be obtained in terms of a G if we are able to solve this problem in the presence of this delta function. Okay, instead of an arbitrary source, if we solve it in terms of the delta function, then our problem will be solved. So this is what we are going to do, therefore. We are going to take this operator and find its inverse, the Green's function that we are going to find, and we want to solve this particular equation with the delta function present. So again, the standard technique to do this would be to take the Fourier transform, as we have seen for the Poisson equation. So we take the Fourier transform, but first we take the Fourier transform. So basically, this is the procedure, just to outline. This is, I think, here I have outlined the procedure. So basically, if we take the Fourier transform on both sides, then the partial differential equation reduces to an algebraic differential equation, which we can solve. So we can solve for the Fourier transform of G, and then we can integrate back to obtain the full solution, right? So, So, So before we proceed, we would like to say one thing here, and that is basically this procedure works completely fine, even in this case, like it has worked for the Poisson equation. So this procedure works even in this case, and what happens is, in that particular step, in the last step, essentially, we have to we have to find an integration, like we saw in the case of the Poisson equation as well. We had to finally take the Fourier transform and find G. In that last step, that involves an integration. Now, the integration here that comes out here, is an integration which is very easy to do using contour integrals. Okay, and I believe some of you in class today, or in this particular class, are not so much familiar with contour integrals. Okay, so if you are not so much familiar with contour integrals, we are going to learn that in the parallel course on mathematical methods. So what I'm going to do is, I'm going to give you a little bit of a handout on that process, okay, doing it with the contour integral process. Okay, but here we will follow Jackson, okay, the description in Jackson, and we are going to you are going to bypass doing that contour integrals with some arguments, which you will see here. So in class, let me use that argument in the same way in which Jackson solves the problem. This Jackson is this Jerry Jackson. It's the book on classical electrodynamics by Jerry Jackson. So that if you see that book does it in a particular way without using contour integrals. And in this video, we will discuss that way. But I will give you a little bit of a handout where this problem is solved using these standard steps. That first you do the Fourier transform completely, and then you solve the equation. So find the Fourier transform of G with respect to all the variables, and then find what is G, and transform back and find what is G. Okay, so that step I will give you as a handout, and you will see that that is a non-trivial contour integrals that would require a little bit of something called pole prescription, etc. And the solution is not going to be unique. Even here, we will see that the solution is not going to be unique. Okay, so we will. But again, for the sake of this video, let's just discuss what the way in which Jackson will do it, and I'll give you the handout separately. Okay, for those who are familiar with contour integrals, are highly encouraged to go through that handout. Very good. Now, if you take this G, then immediately from some physical requirements, something follows. Okay, some property of the G follows. Okay, the thing that we want to emphasize is it should not matter where we have this origin of the delta function is, both in terms of space and time. Okay, so you see that we must be able to shift the origin, and the delta function doesn't depend on it, so the Green's function shouldn't also depend on it. That means if we shift, here, you see this is called translational invariance. that if we shift both r and x by the same vector a, then the delta function remains invariant. Okay, and if we also shift t and t prime with this t naught, then the delta function remains invariant. So you'd expect the g also to remain invariant. So it better be that these two variables in the in G, they appear in this particular combination. Otherwise, then there will be no cancelling out, and it will depend on the if there is any other combination, then it will depend under a shift of origin. Okay, it will depend on this vector a and t naught. Only this condition will ensure that there is no dependence on such a shift. Okay, because the source is invariant under such a shift, so you'd expect the Green's function would also, the source in this case is a delta function. Again, to be specific, this is a 4-dimensional delta function. I'm just not writing the 4 here, just not to clutter notation. This is a 4-dimensional delta function, and so all these things are invariant under this shift of translations, and therefore you would expect the Green's function also to be invariant. So this is a property of the Green's function, that on xt and r and t prime, it should depend in this particular way as the differences. Okay, so that is something which just follows from translational invariance. This is one of the properties. Okay, very good. The other property is basically you would expect the solution to be rotationally invariant about the point where this r is located. Okay, so this delta function clicks at some spatial value of r. Okay, and wherever it clicks, you would expect this to be invariant under rotation about that point. So basically, if you consider, let's say this is the origin, this is the r vector. Okay, so about this point, you would expect a rotational invariance about this point in any direction, and that would tell you that the dependence on x and r, it's not only x minus r, but it should depend only on the mod of x and r. So it will only depend on the distance from this point x. Okay, this is exactly what happened even for the case of Poisson equation, as we've seen, that the Green's function depended only on the magnitude of the distance. Okay, so it doesn't depend on all the vector directions of x minus r vector. It only depends on the magnitude of this distance because of rotational invariance. So let's say this is the r vector. So if there's rotational invariance about this point, it can only depend on the distance from this point. Okay, so that is what this statement is. So rotational invariance implies that G will have the form which is x minus r. Okay, now let us denote this x minus r vector in terms of a r vector. So we will say that this G must be a function of r only, and it must be a function of tau, where this tau is again the difference between t and t prime. So it's just a function of r and tau. Okay, rather than being a function of 4 things, x, r, t and t prime. Okay, so the variables are 4 into 2, that's like 8. Therefore, it just depends on two particular combination of the variables, of the 8 variables. Okay, here we have 3 variables for x, 3 variables for r, t is 1 variable, t prime is another variable. So these are 8 variables in all, but it should depend only on the 2 combinations of the 8 variables given translational and rotational invariance. Okay, so that's what which is implied, and that's what we're going to assume and proceed. At least the rotational invariance part, this you would not have to assume if as we saw for the Poisson equation as well, that this was not necessary if we just followed the usual procedure of converting into Fourier space and doing the integration. That would not require us to use this idea of rotational invariance and the symmetry of this G, that wouldn't have required it. So, so here also, if we just directly do the integration following these steps that I initially mentioned, as you will see in the handout, that would not require this additional condition of rotational invariance. It will just follow from the integration. Okay, but here we will proceed by, these are very physical things, and this should constrain the form of the Green's function. And because these are very physical and it constrains the form of the Green's function, therefore we should proceed without with these assumptions. We can proceed, make our life simple with these assumptions. And so the first thing that we are going to do here is the following: that we can. So this is the equation that we want to solve, right? This is the equation that we want to solve, And as far as this this vector is r. So as far as this r vector is concerned, it is like the shift of x with this small r vector. Okay, so here, as far as this equation is concerned, it is a Laplacian with respect to the x vector, but we can convert it into the Laplacian with respect to the r vector, but by just shifting the variables by this r, if you like. Okay, so you can think of it as just shifting the variables, going to the x and r variable, going to the r and tau variable, through this shift, and writing this Laplacian in terms of the r and tau instead of the x. Okay, so this, if you like, is just a variable transformation. And as far as the x variable is concerned, these are like a constant. This is like a constant shift, and therefore this delta function also becomes this r becomes the location of the delta function. So that is also there. So we just shift it, if you like. Okay. Or in another way, you can also think of it in this way. You can just set the r vector and t prime. You can set it to 0, and then just in that case, the r vector is just the x vector, and in that case, this is a correct equation in terms of the x vector, which is also the r vector. That's another way to think of it. Okay, eventually when you find a solution, then you will use translational invariance and rotational invariance to put in the r and t prime dependence as well. Okay, that you can also do. Okay, you can also think of it in that way. So there are two ways to think of it. Either you shift the variable, or you think that this location is just 0 location, and at the end of the day you can just shift, do the appropriate shifting consistent with rotational and translational invariance and get back the solution. Okay, very good. Now, so finally we have to solve this particular equation, right? Finally we have to solve this particular equation, and because we have to solve this particular equation, let us proceed by doing the Fourier transform with respect to the tau coordinate only. Okay, that's what we are going to do. Okay, so we just do the Fourier transform with respect to the tau coordinate. Okay, so of course this is, as I said, this is a 4-dimensional delta function. So this, if you like, is a 4-dimensional delta function. Okay, so let me use some color. So this is like the 4-dimensional delta function, and we can write this as the 3-dimensional delta function on R. This is what it is explicitly. Okay, and there's a single dimensional delta function on tau. This is what exactly it is. Okay, so this delta function is basically product of 4 delta functions, and this can be written explicitly in this way. So this delta of tau here we can write as the integral of these e to the power I omega tau. Okay, this just follows from the, we have seen that this is the integral representation of the delta function. Okay, and the g of r and tau, we can just take the Fourier transform with respect to tau. Okay, of course this is a function of omega. This omega is the variable, the dual variable. So this g also must depend on omega, but this omega dependence we are writing in the subscript rather than here as a function. It's equivalent. We could have written it as a function also. Okay, and the r dependence will stay as it is, and so we are just doing the Fourier transform with respect to the tau coordinate. Okay, now we can take these two things and plug it back into this equation here. Plug it back into this equation here. Okay, and if we do that, let's see what happens if we plug it back into the equation. So here, this is the thing which was the g, and this is the thing which was the delta of tau. So now if we see that this thing can go inside, because this is just an integration over omega, that's a completely different variable. So we can take this inside, and as soon as it goes inside, this del square del tau square would only hit here, because this is the only function that depends on tau inside the integral, and that will bring down a factor of I omega, 2 factors of I omega. That will give me a minus omega square. That will take care of this sign. The minus sign will become a plus sign, and then this will become omega square by c square. Okay, this acting on the gr function. Again, there can be a omega dependence in this g as well. Okay, on the other hand, so the integral will be there. Of course, the integral will be there, and there will be this e to the power minus I omega t. Okay, that part will be there, but that will be there on this side of the integral as well. Okay, so now you can just compare coefficients of these linearly independent functions e to the power I omega tau minus I omega tau, and if you compare the coefficient of these linearly independent functions, then basically this is the equation that we have, and now we have to solve this equation. Here I can denote this omega square by c square by a square, and I have denoted by a square. Where this a is this omega by c, simply this omega by c. It's actually plus minus omega by c, if you like. Okay, so a square is basically, let's say that a square is basically omega square by c square. Okay, so right. So again, if you like, we are not talking about electromagnetic waves here, but this a is very similar to the k that we had in case of electromagnetic waves, where the k was also omega by c, plus minus omega by c. Okay, so here also there was a, if you like, there was a square. Right. So basically, this is the equation that we have to solve now, and this equation, after doing the Fourier transform on tau, we are reduced to this equation, and this equation has a name. It's called the Helmholtz equation. So we have to solve this equation now, right? So in order to do that, again, we could do the following. We could take another Fourier transform on the R variable, and if we took another Fourier transform on the R variable, this will give me something like k square, and basically, if we say e to the power I k dot R, minus I k dot R, if we just follow that same procedure here, write the delta function out, and then basically this will be an algebraic equation, and then basically this will be given by, essentially, there will be a minus sign out, and there will be 4 pi divided by k square minus a square, where this is the the dual variable of the R vector. K is the dual variable of the R vector. Okay, so this is the algebraic solution, and if we want to find g of R, then we just have to plug it back in here and do this integral. So finally, we have to just do this integral to know what the value of the, we have to just find the Fourier transform and then Fourier transform back. That is the prescription. But again, this integral requires the contour prescription that I mentioned, and you will find this integral solved in your in the handout that I will give you. Okay, but here we are going to try to see and adopt a slightly different procedure due to Jackson. You can see the page, it's given in page 243 to 246 in Jackson. You can consult those pages. And this is what we are going to say. Okay, this is what Jackson tells us to do. Okay, so he tells us that if we take this fact that this G has to be rotationally invariant, then this G cannot depend on the angular coordinates of the Laplacian. Okay, it just depends on R. Okay. And of course, it has a omega dependence. This omega is present here in the A square is omega square by c square. Okay, so now what we can do is we can write the Laplacian out in terms of the radial coordinate only. So it's the radial coordinate in the R space, in terms of the R coordinates. Okay, so if you like, R coordinate has capital R, theta, and phi. These are the three coordinates. But because this function is invariant under the theta and phi, so in general this is R theta phi, but this G of R vector is not a function of theta and phi, but just a function of R. Therefore, the derivative with respect to theta and phi, they will just drop out in this when the Laplacian acts on this. So I'm putting in the assumption of rotational invariance here, the fact that this dependence of the Green's function on R cannot be on the entire R vector, but it has to be only on the magnitude of R. Okay, so that once we put that in, then we can write this Laplacian out. I mean, again, you can look up the expression for the Laplacian, and you can try to massage it a little bit, and you will see that the Laplacian for the radial part of the Laplacian, if this is just dependent on the radial direction, then it can be written in this form: 1 over R d squared dr squared R times G of R. Okay, it's something which is basically can be very useful to remember. If you just remember this form of the Laplacian, this radial form of the Laplacian, then it can be very useful to remember this form actually. Okay, so but anyway, even I don't remember the full general Laplacian in spherical polar coordinates, but this is the part that is it's useful to remember this part. Okay, now if you take this And if you now want to solve for this function g of r, if we want to solve for this function g of r, then you can do the following. You can now solve this differential equation, okay, that you have here. Okay, so before solving the differential equation with the delta function, you can try to solve the homogeneous equation without any delta function. Okay, so if you solve the differential equation without any delta function, this is the homogeneous equation, and then you will see that, look what is happening. You see, in terms of this function r times g, okay, in terms of this combination, this equation is nothing but the equation of a harmonic oscillator, okay, which you know how to solve. So this equation, therefore, r times g, this would admit solutions like this, e to the power plus minus I a r. Okay, again, a is basically omega, plus minus omega by c, but the plus minus sign is here. I have taken that into account here. Okay, so that's very good. So we see there are two solutions to this homogeneous equation, one with a plus sign and the other with a minus sign. So there is a sine and a cos, if you like. Okay, I'm just writing it in terms of the exponential here. Okay, so basically, therefore, the g would be divided, we have to divide by the r, so the g would be given by 1 over r e to the power plus minus I omega r by c. This is the combination that will remain. So this is something which solves the homogeneous equation. Now, if you go back to this equation, you will notice that this equation is this term, right hand side, is always 0 except at the origin. So other than the origin, this term is always 0. So because this term is always 0 other than the origin, therefore, we have actually solved this equation everywhere other than the origin. So this solution that we have written is a good solution everywhere other than just the origin. Okay, so let's see what happens at the origin. At the origin, near the origin, you will see that the origin is basically r tends to 0, that thing. Okay, and near the origin, what will happen, this term will dominate over this term near the origin. Okay, or if you look at, so this you can see clearly because there's a 1 over r here in this term. Okay, this term is going to dominate over this term near the origin, and therefore, if you look at this equation here, you will see that this term, the Laplacian term, would dominate over this a squared term that we had in the equation for the Green's function. Okay, so of course this omega dependence should be there always, right? So this therefore tells us that near the origin, this equation reduces to nothing but the Poisson equation. Okay, that's the Poisson equation near the origin. And as you guys know what the solution to the Poisson equation is, and that the solution to the Poisson equation is 1 over r. Okay, so basically you see near the origin, this is up to, correct up to all numerical factors. Okay, this is 1 over r because the 4 pi I have already, minus 4 pi, that I have already taken into account here in the definition of the Green's function. Okay, so now if this is 1 over r, then if this is 1 over r, then we see that near the origin it's 1 over r. Okay, that's the right solution. And away from the origin, it's just this homogeneous equation that we have here, and whose solution is this whole thing. So near the origin, we have a case where a times r is much less than 1, and if we expand this out near the origin, okay, then we will see that this also reduces to the same 1 over r near the origin in the limiting case. Okay, so basically the problem with the delta function is non-zero only at the origin, in the limiting sense. Okay, and as soon as we reach the origin, this is a good solution, but away from the origin, this is a good solution. So we see that this solution reduces to this solution at the origin if we take the omega r tends to 0 limit, this limit. Okay, if this is much less than r, and therefore this whole solution is now a valid solution everywhere, away from the origin as well as at the origin. Okay, so therefore in this way we have constructed a solution to the full delta function here, So that you can see that we have constructed a full delta function. So so therefore this is a solution to the full equation, right? So right, this is what I have written here. So therefore, given this equation, we can write this solution, which is a solution to this full equation, both at the origin as well as away from the origin. Away from the origin, of course, it is a solution because this is a homogeneous equation and this is a solution to the homogeneous equation. Okay, away from the origin, this equation is a harmonic oscillator equation and it has solutions like this. Okay, we have to divide by r. You know, it's a harmonic oscillator where the variable is r times t. Okay, but at the origin there is a problem. But at the origin also we can forget about this term. It's a Poisson equation, and it has a solution 1 over r. Now this solution also reduces to 1 over r. Therefore, it's a good solution at the origin as well. So this is a good solution everywhere at the origin and away from the origin. Okay, so basically there are two solutions corresponding to these two signs, plus minus, sign. There are two solutions, and these two solutions have a name. The one with the plus sign, as you will see, will justify that name very soon. It's called the advanced solution, and the one with the minus sign. Sorry, the one with the plus sign is called the retarded solution, and the one with the minus sign will call the advanced solution. And the reason for this is as follows. So now we have to find what is G, right? Capital G. Given small g, we have found a solution for the Helmholtz equation, and we have found which is small g. So now we have to plug it back into the time Fourier transform or this tau Fourier transform and find what is capital G. Okay, that we have to do. So we just take this solution, the two solutions together with the plus minus sign, and plug it in this integral with the omega integral. So we have to perform the omega integral and find a solution in terms of tau. So if we do that, so as far as this integral is concerned, this r is a constant. We can just bring the r outside. Okay, but if we look at this expression within the bracket, as you can see very clearly, it is the definition of the delta function. And here what I have done is I have clubbed together terms. So you see this is minus e to the power e to the power minus I omega t. Okay, so this e to the power minus I omega tau, this is here. Okay, and this term is basically plus minus I omega r by c. So this has become minus plus omega I have taken out r by c. So it's omega times tau minus plus r by c, where this r is basically this distance from the location where the delta function clicks, right? So therefore, this combination together is basically now a delta function with the argument which is tau minus plus r by c. That is very clear because this is the integration in terms of omega, and e to the power I omega x, this is a d omega, this is a delta function of x. So but the x here is this combination tau minus plus r by c. And if you remember now, therefore we can write it out in full glory. Okay, the full Green's function, if you like, now you can say that, I'm putting in what this r is. We made a variable transformation. So I'm putting in this what this r is, or you can say that I'm just using translational and rotational invariance to write out the full thing in terms of the original variables. So if you do that, then this tau is basically t minus t prime. Okay, so this tau is t minus t prime, but it doesn't matter. The delta function, delta of x is the same thing as delta of minus x. So again, I have written it in this form. Okay, so right. So yeah. Right. So basically here we have this tau, this thing is basically t minus t prime. I think that was our definition. So so here we have in the argument we had t minus t prime minus plus r by c, and then we just wrote this as minus sign outside, t minus t prime minus outside t minus r minus plus r by c. Okay, so this is a delta function of t prime minus t minus plus r by c, and again, it doesn't, this overall sign doesn't matter because it's a delta function. Okay, so this is the form in which we have written the solution. So the Green's function here itself is a delta function. Okay, so the Green's function is a solution to the equation with the delta function put in, but the Green's function itself is a delta function in terms of the t prime variable. Okay, so if you like, this is just a single dimensional delta function. Okay, this is just a single dimensional delta function. Okay, so yeah, so again, I'm removing this from the notes, just to right. Right. So I hope you understand the algebraic steps, and this is the full delta function that we have. And given the delta function, we can just plug it back and obtain the particular solution, as we discussed initially. That we can write the particular solution immediately in terms of an arbitrary source. So now we are looking at the full equation, the full inhomogeneous wave equation with a arbitrary source. The source is arbitrary. So in that case, we can find a particular solution just by integrating the source with the kernel, which is this Green's function. And now if we do this with the delta function put in, then we see that all it happens, of course, there's a factor of 1 over r. This 1 over r factor, this 1 over r factor remains. There's a factor of 1 over r. But there's something very interesting that happens with the t prime here. So the t prime here gets replaced by, a t tilde, because of the delta function. You are supposed to substitute this t prime with this whole combination here. Okay, this t tilde, therefore, is this whole combination t minus plus distance by c. I'm sorry, I missed a c here. Yeah, so this is distance by c. Okay, so this combination is the combination that has to be put in here. This combination is the combination that has to be put in into this into the time of the source. So you see, the solution at time t is not given by the source at time t, but rather at a time which is different. If you choose the minus sign, then that time is basically some time before, and if you choose the plus sign, then it is a time which is sometime after. Okay, so the one with the minus sign, therefore, is called the retarded solution, and the one with the plus sign here is called the advanced solution. Okay, just note that in our conventions, this thing has flipped. This is minus plus and this is plus minus. Okay, so this is just a bad convention. I think Jackson was following this convention. That's why, it became flipped. But this is a particular solution. Okay, this is a particular solution, and in general, a general solution of the inhomogeneous wave equation is there is a homogeneous piece and then there is a particular piece. This homogeneous piece again is fixed by the initial conditions. This homogeneous piece is fixed by initial conditions, whereas this particular piece, this is fixed by the sources, what the sources are doing, and it is simply given by this integral out here. And as you can see that the time here, this is the main thing to note, the time at which you are interested in the solution. Okay, so here let's say there's a source here, this is the f. Okay, and it's doing various things at different interval of time, and let's say at a distance you are trying to find what this psi is. Okay, the source f is here and the psi is here. So if you want to find this, then you have to consider the f at a time either before or after the time at which you are trying to find a solution here. Okay, so if it is a time which is before, then it is called the retarded solution, and if it is a time after, then it is called the advanced solution. Okay, so this is the main thing, which there are two solutions, one is retarded and advanced. Now here you see there is a condition that comes in. It's like a physical condition, if you like. So eventually what do we want to do? We want to express in electrodynamics, we want to express the potential and hence the fields in terms of the sources. That's what we want to do, right? That is the solution we are finding. Now we can imagine that basically the sources are the causes that produces the electric field. So when the sources dance around, they produce electric and magnetic fields when they move around, and they are the causes. So if you want to find what is the electric and magnetic field at time t, it should be in some sense caused by something which is at a previous time. Okay, in this sense of causality, if you like, okay, if you call this causality, this principle to be causality, that causes happen before the effect. Okay, if you think of this as a principle of causality, that causes should happen before the effect, then naively you would say that the retarded solution is the one which is consistent with this principle or this physical condition, And the advanced solution, the one with the plus sign, is the one which is not consistent with this idea of causality. Okay, because for the advanced solution, what happens? If we are interested in the field at time t, it will be given by a source at a later time. Because of the plus sign, it will be given by the source at a later time. So the effect, if you like, is happening at a later time. The cause, if you like, is happening at a later time compared to the effect, which is the electric field. Okay, the cause, which is the source, is happening at a later time for the advanced solution. So for the advanced solution, the cause, which is the source, is happening at a later time compared to the electric field, which is the effect. Okay, because this is t plus this thing. Okay, so in this sense, it seems that the advanced solutions are unphysical, and therefore we are going to throw them away. So in the electrodynamics that we are going to discuss, we are going to discard the advanced solutions, saying that they are unphysical because they don't comply with this notion of cause having occurred before the effect. Okay, in that sense we will throw away the advanced solution. In everything that we are going to discuss later, after this, we are going to only keep track of the retarded solution and throw away the advanced solution, saying that they are unphysical under this, this idea of cause and effect relationship. Now, I must say that this is something which is, I think, interesting, very interesting, is that there has been, this is a bit of a, this statement of throwing away the unphysical solution, which is the advanced solution, may not be the best way to deal with these solutions. Okay. Because what happens if we do that, then although we'll discuss this again later, you will see that that our theory of electrodynamics is invariant under time reversal invariant. When I'm going to discuss the symmetries of the equation, I will discuss this also, that it is invariant under a t going to minus t. Okay, so I mean, you have to change the fields and the sources appropriately. Okay, basically, if you say that, you can check this as an exercise. We'll discuss this again, but you can check this under t going to minus t. If you say that the electric field remains invariant, okay, the magnetic field goes to minus itself, and the current becomes minus the current. Okay, because if t goes to minus t, if the charge is moving in one direction, then if you reverse time, it starts moving in the other direction. So this is the, if you under this time reversal symmetry, this is called the time reversal symmetry of the Maxwell's equation. Okay, under this symmetry, time reversal. So this is time reversal. So under this time reversal symmetry, the Maxwell's equation remain invariant. But if you throw away the advanced solution, then this is not a very good, this is not a time reversal invariant thing to do, right? So in order to maintain this symmetry in time, in this time reversal, therefore it is, therefore I think there were people like Feynman and Wheeler, who came up with this theory. It's called the absorber theory, where both the advanced and the retarded solutions were kept. And basically, in some sense, the initial conditions were used to pick up, one of these, solutions. Okay, so even in that way of, there's, so basically, but the bottom line is there's a way to keep both the advanced and retarded solutions and still get causal things by setting the appropriate initial condition. And this was the idea of Feynman and Wheeler. But for simplicity, let's not get into that kind of a discussion. And this is also the main way in which most of the books describe this is basically you can think of the advanced solutions as something unphysical and forget about them. And for everything physical, you can only focus on the retarded solutions and then move on. Okay, so that's the point of view we are going to take in this course as well. But it's worth mentioning that there's an attempt, especially by Feynman and Wheeler, most prominently, where you basically, this is called the absorber theory of Feynman and Wheeler, where you can take this, you also talk about, you don't talk about discarding the advanced solution completely, but you say that the solution space has both these kind of solutions, but now there will be initial conditions which will be used to basically select out one of them in some sense. Okay, so basically that is the idea, and so with that, let me now proceed. To the case of electrodynamics. Yeah, so here I mentioned that the retarded solutions are the ones that are to be kept. Okay, so good. Yeah, I just mentioned these things that I've written here, so you can go through this once. And now, so let us come back to electrodynamics. So now, equipped with the fact that we know how to solve the inhomogeneous wave equation, let us look back, what were the equations for the scalar and vector potential we needed to solve. We needed to solve this particular set of equations for the scalar and vector potentials, and now we know the solution to that. So here the source, this I was calling minus 4 pi times f. Okay, so minus sign is already present here. We need to take into account this 4 pi factor, and so divide both rho and j by 4 pi if we want to use that solution. That we do, we keep in track and divide by the factor of 4 pi, and then we just use the fact that it is given by the source at a time t tilde, and to make this explicit that I am using the retarded solution, I have written the word retarded here. So what do I mean by this solution is, you just take phi and t, phi at r and t, then you have to consider the distance, divide by that distance, and then take the source at the point x and at a time which is earlier. So this is like a earlier time. So this is a minus, again there's a minus 1 over c I'm missing, I don't know why. Okay, so this is minus 1 over c. I know why, because I'm very much used to setting c is equal to 1. So but here you don't say, you're working in SI units where c is not 1. So basically this c will be here. So basically this is t equal to t minus this distance by c. That t tilde should go into the source. That is the idea of the retarded solution. Okay, that is what happens. Otherwise, this is exactly the same structure as it was there for electrostatics and magnetostatics. If you remember, it's just this complicacy with respect to this time that was missing, and this complicacy also has this interesting fact that we have to talk about the retarded solutions. It's not the same time t here. Okay, it's the time minus this term, which is the distance from the point to this point. So basically this is the thing. Okay, let me maybe I should draw a little bit of a diagram. You see, let's say there's a charge, okay, doing something at a particular point, which is this position of this charge, you can say, is basically this x vector. Okay, this is some plus q, okay, which is maybe it's dancing around at that point, at the point x vector. Okay, so if it is doing that, okay, we will see. Okay, maybe again it can be a plus charge, it can be a charge density, like that. So we'll do the charge, single charge problem. But in general, you can say that there's a charge at some point, or the charge density. There's some little plus q charge in some extended charge density here. Okay, there's some little plus q, and we are interested in finding the electric field at a distance which is different. Let's say this is at r. Okay, but we are interested in finding phi and a at r and at time t. So if we want to find this value at time t, then we cannot take rho at x at time t. We cannot take that. We have to take it at a time before this thing, and this before is basically this distance r, this distance is r divided by c. Okay, so that's the physical picture, that you have to take the distance divided by c, that part away from this time, and then at the time before that, that time what the source was doing, that would determine the fields at this point. So in some sense, the fields, if you like, they are in some sense, these fields, if you like, they are essentially, you have to, like, if there is a disturbance here, then it will affect the electric field at this point only at a time after r by c, right? So in that sense, where r is this distance, okay? So in that sense, this disturbance here is traveling at the speed of light and reaching this point where the electric field is measured, okay? But this just comes out, there's no electromagnetic wave here, okay? Don't get confused. Electromagnetic wave is a different set of solution, okay? It's not like an electromagnetic wave is being emitted and it's reaching this point. It's just that if anything happens here, it will take, that happening, that the information of that happening will take a little bit of extra time to reach this point here, which is just, and it will travel at the speed of light, if you like. Okay, so that's one of the ways to see, what is going on here. Right. So, right. Let me just place this. Oops. Yeah, I have to. All right, so I'll just place this figure on the same page. Right. Okay, so this is what we have here. Okay, these are the retarded solutions. Therefore, okay, so here by retarded, this thing, I mean that here this T tilde has to be solved from this condition and plugged back in. Okay, that's what I mean. Very good. So now, because we know the potentials, or these are the so-called retarded solution for the potential, because we know that, now we can go ahead and compute the electric field. We know the formula for the electric and magnetic field in terms of the potentials. This is the formula here. Okay, and we can just plug it in, and therefore, you can find what the solutions are. And basically here, this T tilde, this I'm calling T retarded, if you like. This is T tilde, what I've called T tilde before, or T retarded, if you like. Okay, so this is basically this expression out here. Okay, T minus this thing. Okay, so in order to know the electric and magnetic field, we have to algebraically find these gradients, this curl and this derivative. So let's do that one by one. So if you take the gradient of the phi, what do we get? So the expression of the phi was this. Now the gradient is with respect to the r coordinate, because the r, phi has the dependence on r. So we take the gradient on phi, and again this r, because this is an integral over x, therefore the gradient with respect to the r, they just moves inside the integral. And as it moves inside the integral, then we have two terms here. One is in the numerator, this charge density, and in the denominator we have this distance, where also this r appears. Now this is something we have seen before, right? This is something we have seen before, and therefore this gradient can act on this r here, and that will give us this term, where the first one will be minus. So this is a minus to the power minus 1. So this will be a minus this thing square, and then it will be gradient of this quantity. Okay, this quantity out here. Okay, and as we know that the gradient of this quantity is basically the unit vector along that direction. Okay, the gradient of x is basically this unit vector. So that will give us a power of cube, So basically there's a minus 1 here, which will be transformed to a minus 2 because of the first differentiation. And then this differentiation is also giving us a power of this thing below, because this is the unit vector along this thing. So if you write it vectorically, then this is the full vector. As the full vector, then there is a power, cube power here. And this manipulation you have seen before. This is the exact same manipulation as happens in electrostatics. When you find the electrostatic potential, then you take the gradient. It's exactly the same manipulation. Okay, and the electric field is minus of this, so this minus sign drops out, and the electric field is given by, this if you like is the Coulomb's law in electrostatics, if there is no time dependence. But now there is this retarded time, and as you can see here, functionally, there's an r dependence here on which this gradient can also act, and it will act. So if you apply chain rule, so this is again the R, this is again the R gradient. So this is the R gradient. So if you apply chain rule, then this will the first will be the derivative of t tilde with respect to this, and then it will be the gradient of t tilde. So if you like, I can just make the retarded into t tilde. Now that's what I mean by retarded. Okay, time. Okay. So this t tilde is given by this expression. So now we again have to take the gradient of this thing, which is again the same expression, but apart, now there's a minus sign which is here. Okay, there's a minus sign which is here. Okay, this minus sign comes from this minus sign here from t tilde definition. Okay, and then there is this thing becomes the unit vector. So this thing gets another power because I've written as a vector. If I had written a hat here, then this will not be just 1. Okay, even if I written hat here, then this will be just 2, and that is Coulomb's law. Okay, but apart from Coulomb's law, the usual thing, there is now another term like this, which basically depends on the time derivative of the rho. Okay, but this time derivative of rho is not at any time. It is not at the same time as the time here appearing on the left hand side, but it is at a retarded time. So we have to take the derivative and then set. So if you like, we can actually we can put a tilde here. So we have to take the derivative with respect to the tilde and then set t tilde equal to this t minus this thing, t minus r by c in this differentiation here. Okay, so basically there are two terms in the gradient of phi. Okay, there are two terms in the gradient of phi. So minus the gradient of phi has these two terms. So if for compactness of notation, if we denote this relative vector by this r hat, r vector, capital R, then this is just simply r hat divided by r square, mind you. This is cube because I have written it this as r vector. Okay, but this is r hat. This r hat itself, if you like, is this thing, right? So this r hat itself is this vector r vector minus x vector divided by mod of r vector minus x vector. It's the unit vector along that direction. Okay, so this r hat is that. So that takes away this one of these powers. That takes away one of these powers. This denominator would take away one of these powers. So this is r hat by r square. Again, Coulomb's law, it's r hat by r square. This is Coulomb's law. Okay, but apart from Coulomb's law, there's this term as well, where there's a t tilde, and the t tilde must be obtained by solving this retarded condition in terms of t. So t tilde is basically t minus r by c. Okay, so here t tilde is basically t tilde is basically t minus r by c. And what is this t? What is this t? This t is the same t as this one. Please remember this. So this t is the same t as this t out here. Okay, so that is very important. Okay, so with this we will now look at what is the time derivative of a. Okay, so this is again with respect to t and not t tilde, right? Because there is only one t dependence here. Okay, so if this is a derivative with respect to t, then we will just take, we know that t tilde is given in terms of t by this relation. Okay, and this time derivative would go inside the integral. Okay, because if you know that this is the thing, the integral of this was the thing which is a. So I've just taken the time derivative inside the integral. This is another term in the electric field that we need to find. So we have taken the time derivative inside the integral, and this t dependence is only there in t tilde because t tilde is t times this. So if you now just perform chain rule, like, so this will just become the derivative with respect to t tilde, right? Because del t is basically del t tilde, del t tilde del t, and del t tilde del t is basically 1. Okay, if you like, let me also write here. So if you like, del t tilde del t is equal to 1, and therefore you can just write this directly. But the retarded condition has to be kept in mind. You have to take the derivative with respect to t tilde and then set t tilde equal to that, this quantity here. Okay, but you can take the derivative with respect to t or t tilde, doesn't matter. You just have to put in the retarded condition. Okay, so therefore this is just a time derivative of j that comes in here through the time derivative of a, and so again the 1 over r remains as usual, and this is the time derivative of j under the retarded condition. Okay, And then there is a minus sign here because in the expression for the electric field, there is minus del A del T. Okay, that's why the minus sign. Okay, so now basically the electric field is basically combination of this term, these two terms, and this term. So there are like three terms in the electric field. Okay, we'll write it down compactly now. But before we do that, again, let's look at the curl of A. Okay, let's also look at the curl of A. So the curl of A, if we want to find, again, this is a R dependence here. So the curl is with respect to the R coordinate. And we can take this curl inside the integral like this because the differentiation, the integration is with respect to the X coordinate. And once we take the curl inside, then of course the derivative here can act on the R here. And that is exactly what happens in Biot-Savart's law, you know, the one that gives you the Biot-Savart's law in magnetostatics. Okay, so this expression, this, if you like, go back and check Biot-Savart's law, and you will see that again, you know, there's a derivative on here. So there's the -1 becomes a -2, and then this R hat becomes crossed with the J, essentially, if you do the manipulations. Okay, so just go back and check, you know, how Biot-Savart's law was derived. That is exactly the same step as in magnetostatics. But here there is again another more complicacy because there is a R dependence in the T tilde as well. Okay, so since the R dependence is there in the T tilde, this term has to be massaged. So this curl, I have written it down in the epsilon, and then this is T retarded or T tilde, if you like. It's the same thing that, you know, that I'm using interchangeably. So this is T tilde. Okay, this T tilde is nothing but T minus R by C. Okay, so that's the T tilde here. Okay, and if you again, now if you differentiate this, we will simply see that there's a time derivative. Of course, this is chain rule, so that's why we have the, you know, so this is how T tilde came in here. So like, you know, del T tilde, you know, this curl's derivative, you know, that is what is going to remain here. And then this is, you know, here from here, there's this R by C on which this derivative is going to be there. And that is exactly going to give us a R hat out here. And this factor of C will remain here, this factor of C. Okay, let me check if I have taken into account the right factor of C in the del. So this del T is very clean. There's no like, you know, so this del T, as far as this del T is concerned, you see there was a mu naught here, and mu naught I've converted into epsilon naught. Then therefore there's a factor of C here. Okay, C square here. So if you like, C is equal to 1 over root over mu naught epsilon naught, and therefore mu naught is equal to so square it. So mu naught is equal to 1 over epsilon naught C square. Okay, this is something which we have used here. Out here we have used that fact, and you know, we can take the 1 over 4 pi epsilon naught common in the expression for the electric field. And here here also there is a, you know, when we took this derivative, if you remember, then there was this factor of C here. This factor of C came from the fact that there's a R by C. So when we take this derivative here, then this is given by R by C, and therefore that is that factor of C here that remains in this final answer, this factor of C. So here there's a factor of C. In this term there's a factor of C squared, and here also in the curl term, you know, that term there's a factor of 1 over C, because, you know, this becomes R hat by C. This derivative gives you R hat, and if you put the epsilons together, then this gives you a cross product between this and this. Okay, with the right sign. You can check the sign. Okay, so this is given by C times R hat. This C is basically comes from this C in the expression for the retarded time. Okay, so therefore curl of A, putting everything together, has two terms. This is the usual Biot-Savart's law, and this is the one that has the 1 over, you know, that is a new term which depends on the time derivative of this J. Again, the time derivative is with respect to T tilde, but at the end, after doing the derivative, you have to set T tilde equal to T minus R by C, where that T is basically this T. Okay, so please remember that. So the electric field, therefore putting things together, has three terms. One is this Coulomb's law, but then there are two other terms which are the time derivative terms that are present only in case of electrodynamics, where there is time derivative, otherwise it's not there. And the magnetic field here has just two terms. One is this Biot-Savart's law, okay, which we have seen. Okay, even in the present, but again, even in Biot-Savart's law, there is a difference. You know, this is not happening at the same time. Okay, if there is no time dependence, then, you know, you can forget about this T tilde. But if there is a time dependence, then the time dependence here is basically not the same time dependence in the source, but this is at a this is the source at a different time, at a time before. That is why it's the retarded solution. Okay, so this is why it's a retarded condition. And again, there's an additional piece compared to the Biot-Savart's law, and this additional piece is basically this piece due to the time derivative on the current density, and again that retarded condition must be maintained here, and so this is the thing. Okay, again let me write down here. So this T tilde is nothing but T minus R by C. Okay, that is something important. So this electric and magnetic field, therefore, we have solved completely in terms of localized sources like the charge density and current density. We have solved the electrodynamic problem completely as far as the electric and magnetic field is concerned, as far as the retarded solutions are concerned. Okay, and this particular way of writing the solutions down, this has a name. It's called the Jeffimenko solution, and it was written down compactly by this person. And so this is called the Jeffimenko solution, which is a generalization of the if you like, it's a generalization of the Coulomb law, and it's a generalization of the Biot-Savart's law in magnetostatics and the Coulomb's law. Okay, that is generalized to this general solution in this way. Okay, very good. So so that is all I have to say. The only thing that I want to stop here before stopping, I want to mention is this. Look. This fact out here, this goes as 1 over r square, 1 over the distance square. It's like the Coulomb's law, as I said, like the point charge, like it happens for the point charge. But if things are moving around and things depend on time, the charge density depend on time, then there can be also another factor which goes as 1 over r. Okay, so this fall off is slow compared to the fall off of a point charge. Okay, and this can happen only if there is time derivative. Even this fall off is small. Okay, this goes as 1 over r. Okay, even here for the magnetic field there is a term which goes as 1 over r. Okay, this is the usual Biot-Savart's law where the magnetic field goes down as 1 over r squared. But here there is a magnetic field which there is a term which depends on the time derivatives. These terms which depend on time derivatives particularly, there can be such terms arising out of these terms which fall off at a slower rate as 1 over r compared to 1 over r squared for the case of, let's say, a single current carrying conductor or a single point charge. That has a fall off which is 1 over r squared. That fall off, there can be terms which fall off even more slowly than that, and therefore this influence would reach farther and farther distances. Okay, so but this will see that these terms which goes as 1 over r has a very important implication for radiation coming out of an arbitrarily moving source. When we are going to discuss radiation in after 2 videos, we'll see that these are the terms that play a very important role in radiation, and that's what I wanted to give you a little bit of a prelude. And let me stop here for this video. Okay, so we have written down the full solution for the electrodynamic problem. Given an arbitrarily localized charge density and current density, we have found the electric and magnetic field as an integral, and now given any kind of given source, we can just take this, and if we are able to find this integral, then we know what the electric and magnetic fields are. So we have solved the differential equations in that sense. Okay, so as we have seen. So let me stop here for this video. Yeah, thank you for your attention.